Drivability problems. You know, rough idle, low power, hesitation, hard starting. Now, you technicians spend a lot of time on those problems. Many of them are mechanically based, and you're familiar with the remedies. And of course, their diagnosis and repair and replacement procedures are thoroughly covered in your service manuals. I don't have to tell you that whenever your truck customer presents you with a drivability problem, you first need to look to the traditional mechanical approach for the solution. But don't ignore one of the most important sources of drivability problems: fuel. Yep, fuel. Now, whether we like it or not, the fuel that comes out of this nozzle has a direct effect on the drivability of our trucks, often creating problems that we then have to deal with to keep those trucks operating properly. Fuel is one of the most basic things that you look for when you're troubleshooting an engine. You know the questions. Do you have compression, spark, and fuel? But then there's a natural tendency to forget about fuel once we have it. But the fuel that's in the truck when it comes into the shop may need a much closer look, especially a truck with a drivability problem. Well, you know, those difficult to solve problems, because often all of the vehicle systems seem to be operating just the way they should. But you know that the complaint is valid because the problem was there when the truck was road tested. Now, this video presentation will cover both gasoline and diesel engines, their fuels, and the drivability problems that each of their fuels can cause. Now, since gasoline and diesel fuels are significantly different, we'll break them apart and look at them separately. As you know, the vast majority of the trucks that GM Trucks sells are gasoline-powered. So we'll discuss gasoline first and then move on to diesel fuel. Now, we'll be looking closely at the properties of those fuels, their additives, and the drivability problems they cause. We'll even touch on the regulations of the federal government and how their impact on fuel affects us and the trucks we service. To start the discussion of gasoline, now let's look at what is supposed to happen inside this engine when the right fuel is introduced. The best case situation. What we want in a gasoline engine is a liquid hydrocarbon fuel, gasoline, that vaporizes when mixed with air, combining completely with the oxygen. If that was all that happened, it would be great, because our chemical formula would be the fuel, primarily made up of hydrocarbons, HC, plus air, oxygen, O2, and nitrogen. When combined at the proper ratio of 14.7 pounds of air to 1 pound of gas and combusted, all that would be emitted out of the chamber would be water, H2O, carbon dioxide, CO2, nitrogen, N, and some oxides of nitrogen, NOx. Good stuff, mostly harmless. But we all know that's not all that comes out. If the air-to-fuel ratio is set incorrectly, the emissions from the exhaust will be significantly different. If the mix is too rich, let's say 12:1, you have too much fuel, too many units of hydrocarbon, and not enough air, or oxygen and nitrogen. After combustion, what remains isn't so good. Sure, you get some of the good emissions, H2O, water, CO2, carbon dioxide, and N, nitrogen, but you also get the unacceptable ones, unburned hydrocarbons or vaporized gasoline, and carbon monoxide, a tasteless, odorless, poisonous gas. If the mix or ratio is too lean, let's say 16:1, or 16 units of air to 1 of fuel, the combustion yields water, carbon dioxide, the good stuff, but you also get nitrous oxide, which creates smog. Now, both of these problems, fuel mixture too rich or too lean, can be corrected by reestablishing the 14.7:1 air-to-fuel mix. Now, that's the end of our drivability problems, right? Wrong. Because gasoline isn't just hydrocarbon. It isn't even just one kind of hydrocarbon. Let me show you what I mean. The crude oil from which we refine gasoline contains everything from methane, butane, and propane, producing high volatility, low heat or energy content fuel, to tar and asphalt at the low volatility, high heat content end of the hydrocarbon scale. Crude oil contains a lot of other compounds too, undesirable ones, such as sulfur, soluble metals, acidic corrosives, basic caustics, and even helium, which is sometimes removed and sold to fill balloons. Crude oil is indeed a very appropriate name for that witch's brew from which we get gasoline and diesel fuel. Petroleum refineries use a simple method to get the various usable petroleum components separated from this brew: distillation. And while the explanation I'm going to give you is simplified, it will help you understand what gasoline is and how it can give us problems. To distill or refine crude oil is to put into a container and heated to boiling. The vapors of this brew travel up a temperature-controlled condensation column. Different compounds then condense out of the vapor at specific points where they are removed from the column. Starting at the base of the distilling column, we find asphalt. Asphalt has such a low volatility or ability to convert from liquid to gas that it won't even boil. It's ultimately removed from the bottom of the still container after all of the other components have been boiled off. As we move up the column, our heated vapor begins to cool. The heavy components, like grease and gear lube stocks, condense out first. Continuing up the column, more stocks are removed: engine oil, kerosene, diesel, and jet fuel. A little further up, and even cooler, the gasoline, naphtha, and lighter fluid stocks appear. Finally, at the very top of the column are the components that tend to remain a vapor, even after cooling. Components such as methane, butane, propane, and other natural gases. You probably noticed that I referred to these components as stocks. Well, this is because they're not yet in their final form. At this point, we only have the basic building materials that now need more processing and blending, and many of the undesirable elements, like sulfur and corrosives, have yet to be removed from the stock. Not only will the refinery try to get the unwanted materials out, they'll mix or blend additives in. Additives such as octane rating enhancers, oxidation inhibitors, detergents, and corrosion inhibitors. In addition to the additives, they'll mix or blend various gasoline stocks together to get the desired gasoline product. Let me give you an example. A vaporized stock that condensed out of the distillation column at 60 degrees Fahrenheit wouldn't be able to vaporize and thus burn on a cold 30-degree Fahrenheit morning. So what happens? Our trucks won't start. But that same 60 degrees Fahrenheit stock would actually boil in the gas tank on a 90-degree day. You would have a tank full of vapor lock just waiting to happen. To overcome this problem, the refinery blends in minus 20-degree stocks like propane with 0-degree stocks, and then they add 10, 40, and 100-degree stocks to try to hit a happy medium, to produce a gasoline that contains stocks of different volatility that will vaporize across the entire temperature range for a specific time of the year. Being careful not to have a mix with such high volatility that vapor lock becomes a problem. They mix winter blends of gasoline that vaporize easier in cold weather because they contain stocks that have a high volatility. And then there are summer blends, lower volatility and high altitude blends. That load of bad fuel you got early last winter may have just been the last of the gas station's summer blend. You got low volatility fuel just when your truck needed a high volatility fuel. Even if your engine is given the right fuel mix and is burning the fuel at the correct air to fuel mixture, 14.7 to 1, there still are enough emissions that the exhaust pipe emissions are regulated by law. What are those emissions? Well, they break down into three categories: hydrocarbons, HC, carbon monoxide, CO, and oxides of nitrogen, NOx, the big three. Hydrocarbons, HC, are very simply gasoline that didn't burn during combustion. Then there is CO, carbon monoxide, which is gasoline which partially burned. There just wasn't enough oxygen available during combustion to bond with the carbon monoxide for the formation of carbon dioxide. And the third class of federally regulated emissions are oxides of nitrogen. They're simply the result of the combination of oxygen and nitrogen. And these nitrous oxides are the main components of smog. Here's what happens. Remember, you need a 14.7 to 1 mixture of air to fuel to maximize the combustion of the fuel. One reason that the engine requires so much air, 14.7 pounds for each pound of gasoline, is that air is only about 20% oxygen and 80% nitrogen. Normally, oxygen and nitrogen don't combine unless they're subjected to high temperatures, around 2,700 degrees Fahrenheit. Unfortunately, we can have those high temperatures during combustion. To prevent this problem, we use the EGR valve to control the combustion temperature to a point below the combining temperature of oxygen and nitrogen. Well, therefore, when you find high nitrous oxide levels, it could mean a plugged EGR valve or an inoperative EGR. The combustion temperature is too high, allowing the oxygen and nitrogen to combine, forming nitrous oxides. Analyzing emission levels can help you diagnose an engine performance problem. To do so, use your Tech 1 or engine analyzer. Any leading analyzer will measure the levels of 2 of the 3 emission types, hydrocarbons and carbon monoxide. Unfortunately, nitrous oxide levels can't be measured on equipment routinely found in dealerships. Let me give you an example of how the emissions will help you locate a problem. If the emissions level of hydrocarbon is too high, you know that the burning or combustion process is not even starting in a cylinder or cylinders. You have unburned gasoline vapors coming from either a misfire or another source that causes or allows the hydrocarbons to remain unburned. Now, on the other hand, high carbon monoxide levels indicate that only partial burning is taking place. Some combustion occurred, but it was not complete for some reason. It could be too rich a mixture or a leaking exhaust valve. The no burning and some burning conditions are the indicators of where to look for the problem. Another area that is federally regulated is the Corporate Average Fuel Economy, or CAFE. The regulations on miles per gallon have forced the use of engines that use fuel more efficiently. A pretty good approach, but it can create a problem. Our truck customers want their trucks to perform. The only way to meet the government regulations and satisfy our customers' demands of performance is through very precise control over a fuel that itself can be very imprecise. This leads us to our first customer drivability concern, poor performance. Now, there are many things that cause poor performance or low power, such as low compression, worn cam lobes, an out-of-time cam, incorrect base ignition timing, and incorrect or poor fuel. While we're going to concentrate on the fuel, don't forget to make sure that you have ruled out all of the mechanical reasons first. One fuel-related cause of low power can be a fuel with too low an octane rating. The octane rating is a way to measure a gasoline's resistance to burning. The higher the rating, the more resistant the fuel is to unintended ignition, specifically spark knock. To understand what's happening in a spark knock condition, we must look inside the combustion chamber. With the intake stroke completed and the piston nearing the end of the compression stroke, TDC or top dead center, the spark plug must start combustion so that it will be complete by the time the piston is started moving down for maximum heat expansion, providing the greatest downward thrust on the piston. Well, that's what happens when everything is performing properly. But if combustion starts too late, the piston will have moved too far down in the cylinder and the connecting rod to crankshaft angle will be too small for an effective push. The engine couldn't take advantage of the power created by the combustion of the fuel. The result is almost no power. So proper ignition timing advance, up to 30 degrees of crank rotation is needed. As the spark plug ignites the air and fuel mixture, the flame burns rapidly and smoothly across the combustion chamber. As it does, the temperature and pressure start to compress the remaining unburned air and fuel as the piston nears the end of the compression stroke, or TDC. If the remaining fuel and air get so hot that they explode rather than burning smoothly, the ping or spark knock can be heard. The ping or spark knock will be heard not only by the driver, but also by the knock sensor. It will sound like this. The knock sensor then sends a signal to the control module, the ECM, PCM, or VCM. To prevent further pinging and possible engine damage, the control module retards the timing. With the timing retarded, meaning the combustion starts later in the sequence, there is a noticeable loss of power because the engine failed to effectively use the power created by the combustion, and the customer has a valid complaint. A good example of a problem caused by the fuel put in the tank. In this case, fuel with too low an octane rating. A quick road test with a scan tool to monitor the NOx signal can verify the problem. Accelerate the warmed-up truck. If the NOx signal changes from no to yes, then change the Tech 1 to look at the timing advance while repeating the acceleration. If the no response doesn't change to yes, there is another problem, one not related to octane rating. Now, if the timing changes a lot, say 20 to 25 degrees, then a fuel with a higher octane rating may be needed to correct the problem. The higher octane fuel has more resistance to uncontrolled exploding, allowing the combustion to be completed as a smooth burn across the entire combustion chamber. The manual that accompanies this video covers the issue of octane in far greater detail. Be sure to read it thoroughly. Oh, the solution? Simply tell your customer to try a higher octane fuel. That should solve their problem. The octane rating of fuel is increased by blending the gasoline with higher octane stocks or through the use of octane-enhancing additives. We started using additives in the 20s when it was discovered that tetraethyl lead could help stop the spark fuel knock that was present when compression ratios approached 5:1. The lead additive allowed high compression engines to become a reality. Compression ratios then increased to 8:1 in the 1930s and progressed on to 10:1 by the 1950s as the gasoline improved. As you know, the use of tetraethyl lead to increase the octane rating is being phased out, replaced by better blends of gasoline that perform in the same way, meeting the auto manufacturer's needs while satisfying the government regulations. A final point before we leave the subject of octane. Many drivers feel that they will improve engine performance while doing their engine a favor by using a gasoline with a higher octane than the one recommended by the manufacturer. Caution your customers against this practice. Higher octane fuels may not improve engine performance, and your customer certainly doesn't need to pay more for their fuel than they have to. It's important to reference the owner's manual for the correct fuel octane requirements. And a final note on engine spark knock and octane. Don't forget that any mechanical knock in the engine will be picked up by the knock sensor, instructing the control module to retard timing even though the octane level is correct and the fuel isn't prematurely detonating. So when tracking a spark knock condition, be sure to rule out all mechanical sources that could trigger the knock sensor. Before we get back to more drivability problems, I should talk about another additive that you'll encounter. This time, one to improve emission quality. It's MTBE, or methyl tertiary butyl ether. MTBE is used because it blends with gasoline while it adds oxygen. The additional oxygen combines with the hydrocarbons when needed to help complete the conversion of the hydrocarbons to water and carbon dioxide. Remember, when the hydrocarbons aren't completely burned off during combustion, the resulting emissions include unburned hydrocarbons and carbon monoxide, both pollutants. The addition of oxygen-carrying additives, such as MTBE, has been used in some high-pollution areas, such as Denver. More detailed information on MTBE is in your reference manual. A comment about additives and some poor fuel stocks. They can turn into solids during combustion and form deposits in the combustion chamber. These deposits will reduce the volume of the chamber and increase the compression ratio. The higher compression ratio will require a higher octane rated gasoline. The combustion chamber deposits will look like this. To improve drivability, these deposits should be removed. Top engine cleaner may help remove these deposits, but if it's a high mileage engine, the deposits have taken a long time to build up and more than one treatment may be needed to remove them. There are more reasons to be sure that there are no combustion chamber deposits. The hot deposits can trigger unintended fuel detonation or pre-ignition. Another reason for a low power complaint can be a restricted air fuel flow. just not enough fuel and air getting into the cylinders. If a fuel does not vaporize completely, it can be deposited in the hot intake manifold passageways. It will look like this. Note the dark areas. Fuel is baked on these surfaces. For optimum performance, all of the surfaces of the intake manifold should be shiny and not discolored. And on the manifold side of the intake valve, forming varnish and carbon deposits. Remember earlier when I mentioned the precise control of fuel? Well, it applies to the air and fuel flow into the cylinder as well. The 4.3 central port fuel injection manifold is an excellent example. Even small intake deposits can change the airflow pattern and cause a noticeable loss of performance. In addition to changing the flow, porous intake deposits can temporarily absorb gasoline, leaning out the air and fuel mixture and then give up the gas, enriching the mixture. The rapid changing of the air to fuel ratio is not conducive to a smooth running engine and can create a hunting or up and down idle. Anything that reduces the amount of fuel and air getting into the cylinder means less heat is produced during combustion, and less heat means less power. There are basically only 3 ways to remove the intake deposits. There is the chemical method, using top engine cleaner. Now this should be recommended first. If that fails, or you don't think it can handle the deposits, try walnut shell blasting the intake valves. And finally, if these steps are not successful, the heads must be removed from the engine and the deposits mechanically removed with a wire brush as outlined in the service manual. The owner should then change brands of gasoline, preferably to one with a high detergent content. The different fuel should prevent future deposits and restore engine performance. Now, on to a different drivability problem, one of misfiring. Now, a misfiring complaint can also be caused by fuel problems. The additive deposits that can form in the combustion chamber can also foul spark plugs, causing a misfire. And water contamination can also cause an intermittent misfire. If small quantities of water get injected into the combustion chamber in place of the fuel, well, the engine will misfire for an obvious reason. Water won't burn. Since water is heavier than gasoline, it will collect in the bottom of the fuel tank, just like it does in this flask. Then braking, acceleration, or cornering can cause the fuel pump to pick up a small quantity of water and send it to the injectors, creating the intermittent misfire. A note of caution when dealing with water in the fuel. Now, many of the gasoline drying agents, commonly known as dry gas, are primarily alcohol, because alcohol readily mixes with water. Adding these drying agents to gasoline, which may already contain 10% alcohol, can push the fuel's new alcohol content to a point over which the control module and injectors can compensate. So be sure to follow the manufacturer's recommendations carefully. Also, since the alcohol has about 1/2 of the heat or energy content of gasoline, the driver can notice a loss of power when using an alcohol-based drying agent. And finally, too much alcohol can also cause a tip-in hesitation or sag in acceleration. A final comment on removing water from the system. Occasionally, technicians will erroneously substitute injector cleaner for a drying agent. Don't make this mistake. Injector cleaner is exactly that, a cleaner of injectors, and is not intended for removal of water. Other fuel-related causes of hesitation and sag can be a tank full of low-volatility summer fuel during the first fall cold weather. Now, I commented on this earlier. The summer fuel resists vaporizing in the cold, and since a liquid will not burn, the actual air-fuel ratio available to the engine is lean. Even though the right amount of fuel was injected, it just didn't vaporize. Changing gasoline to a winter blend will solve the problem. Now let's move on to another fuel-related drivability problem, rough idle. Rough idle complaints can be the result of fuel deposits on the throttle plate and in the throttle bore area. Now, these deposits are from impurities in the fuel which are left behind as the fuel starts turning into a vapor. The impurities can be the result of blending in too much of the heavier, low-volatility gasoline stocks. As the heat from the engine bakes these deposits in place, they restrict the air-fuel flow, lowering the base idle speed and causing even more deposits in the throttle and manifold areas. An aerosol choke cleaner, GM part number 12345109, will chemically attack and remove the deposits, restoring the correct air-fuel flow. Rough running and rough idle can also be caused by a heavier fuel being added to the gasoline, either accidentally or on purpose. Some unscrupulous gas station operators may mix 100 gallons of 60-cent per gallon gas to 1,000 gallons of $1 per gallon gasoline and sell the 1,100 gallons of gas at the $1 per gallon price, pocketing the extra $400 profit. Well, this practice is not legal. It does happen. And recently, a number of Michigan independent gas stations were heavily fined by the state for selling 87-octane regular gas as 89-octane mid-grade. Rough running and hesitation can also be caused by deposits building up in the fuel injectors. These deposits can affect the injector performance in two ways. First, they can restrict the fuel flow to the point that the engine control module cannot compensate fast enough and briefly causes a lean air-fuel mixture. Now, this is most noticeable when accelerating because there will be a hesitation or tip-in stumble or a sag. Now, this feels like an accelerator pump problem in an older carbureted truck. The other way that injector deposits cause a problem is when they change the spray pattern of the injector. First, if the fuel is released in a dribble rather than a spray, it will not vaporize completely. While the correct amount of fuel may have entered the engine, the non-vaporized fuel will not burn, with the resulting combustion being rich. And second, if the deposits alter the injector's spray pattern in such a way that the fuel is sprayed onto a metal surface instead of into the airstream, the fuel will not vaporize correctly, and a lean, burnable mixture will result. Both the partially vaporized and altered spray resulting from deposits in the injectors will cause problems because we've lost the precise control of the fuel for which the engine was designed. Now, if you discover that the injectors have deposits that are affecting their performance, GM does not recommend cleaning. They need to be replaced. Now let's move on to another drivability problem, hard starting. Now, hard starting, either hot or cold, can be caused by a variety of mechanical or electrical problems, which should be checked out first. Well, such as the performance of the coolant temperature sensor and the MAP sensor. The fuel pump relay and crank signal inputs into the control module must also be correct. Now, once you're satisfied that those factors are correct, look to a fuel problem. Now, the most common problem tends to be the wrong seasonal blend of fuel. Now, I briefly touched on gasoline volatility and the summer, winter, and high altitude blends earlier. A summer blend of low volatility stock is what the truck needs in hot weather conditions to prevent the vaporization of the fuel in the tank. But on a cold Minnesota morning of 10 degrees below zero, there will not be enough of the gas vaporized for the engine to start, or at best, it will be hard starting. Now, on the other hand, the winter blend that was intended to vaporize on that cold Minnesota morning is not going to be what we need on a nice Louisiana 95-degree afternoon. The fuel will vaporize in the fuel tank, fuel lines, and even in the injectors. Remember, fuel vapors don't act like liquid fuel and will produce a classic case of vapor lock. Now, the fuel pump can't get enough fuel to the engine because the pressure regulator and injectors can't pass enough vapor to clear the fuel lines. At best, we would have a hard start hot problem. At worst, no start at all. While the two examples that I just gave you are extremes, both problems can occur almost anywhere in the U.S. if you're dealing with the wrong blend of fuel. Well, we've been discussing vaporization. The vaporization properties of gasoline can be measured. The Reid vapor pressure method is the petroleum and automotive industry standard for the measurement of gasoline volatility. Now, you can test the Reid vapor pressure, or RVP, if you have the Kent-Moore Gas Quality Analyzer Kit, part number J39383A. Pour a small amount of gas into a small plastic container and pack the container in ice. Fill the thermos cup with hot water. above 110 degrees Fahrenheit. Now pour the chilled gasoline into the gauge chamber assembly and put it into the hot water. Place your finger over the thermometer hole and shake gently. Hold the unit upright and gently tap the gauge. Repeat this step until you get a stable reading. That's the vaporization characteristic of the fuel sample. A reading of 7 or 7.5 indicates a low vaporizing characteristic, whereas a fuel with a high PSI of 13 or 14 indicates a fuel of high volatility. The read vapor pressure check is covered in more detail in your reference manual. Now, if you suspect fuel problems, especially in the spring or fall seasons when the temperature changes are more pronounced, you may want to have the Kent-Moore kit handy to verify that the problems are fuel and not truck related. Another customer drivability complaint that can be related to fuel is run-on or dieseling. Now, this is usually caused by too much fuel and air getting into the engine after the ignition is turned off. Now, if the idle is set too fast on carbureted trucks, the extra fuel and air would compression ignite or be ignited by hot combustion chamber deposits, thus causing the run-on or dieseling problem. While the electrical shutoff of the fuel injectors on the newer trucks would seem to prevent this condition, leaking injectors have kept the problem from disappearing. If run-on or dieseling is a problem, it will be necessary to find out where the extra fuel and air are coming from and correct the condition. To eliminate dieseling or run-on, high idle settings need to be corrected, leaking injectors cleaned or replaced, and combustion chamber deposits should be removed. The solution to all of these fuel-related problems is good gasoline. While it's almost impossible to determine the quality of a fuel when purchasing it, the way an engine runs and performs is the real test. As I mentioned earlier, you should suggest that your truck customers change to a different brand of gasoline if they're experiencing the kind of drivability problems that we've discussed. Now, those of you who are near a refinery may have noticed that the mobile tanker, the one from Amoco, the local tanker, and the no-name independent trucks all pick up gasoline at the same loading dock. Don't assume that they're all picking up the same gasoline. The gasolines are not necessarily the same, since the refinery does sell a wide range of gasolines. The no-name tanker may pick up the cheap stuff that has only a small amount of detergents and a little anti-icing compound. The next truck may specify more additives, and the next one may order the best that you got, plus the super deluxe detergent additive package. Well, they and your truck customers do tend to get the quality of gasoline that they pay for. Well, that pretty much covers the most common drivability problems associated with gasoline. Now, let's move on to diesel fuels and their unique characteristics. But first, we need to review the operation of the diesel engine itself. Unlike gasoline engines, diesel engines must fill the cylinders full of air on every intake stroke. Now, a full cylinder of air is needed so that adequate heat is generated on the high 21-to-1 ratio compression stroke. Now, this animation will give you an idea of what's happening inside the typical diesel engine. During the intake stroke, the intake valve opens while the piston moves downward. The action of the piston and the turbocharger, if equipped, causes the air to move into the combustion chamber. The air intake valve closes, and at the end of the intake stroke, the fuel injection pump delivers fuel through a pipe to a nozzle located in the pre-chamber. Then the nozzle opens, spraying fuel into the hot, swirling air in the pre-chamber. The heated compressed air-fuel mixture now achieves combustion, and the expanding gases push the piston downward, the power stroke. Does that type of sparkless combustion sound familiar? Sure. It's like spark knock in a gasoline engine. It's an explosion caused by compressed fuel and air. But in the case of the diesel engine, this explosion is what's supposed to happen. Unlike gasoline, which must resist premature burning, diesel fuel must burn easily when exposed to heat. The cetane rating of diesel fuel is just the opposite of the gasoline octane rating. Where the higher octane is more resistant to burning, the higher cetane rating indicates that the fuel is easier to burn, thus more desirable for a diesel engine. Like gasoline, there are different blends of diesel fuel for winter and summer use. Number 1 diesel fuel, the winter grade, will burn easier than number 2 diesel, the summer grade. Now with number 1 grade fuel, less heat is generated during compression because of the cold weather. But this easier burning fuel is needed for easy starting. As with the gasoline-powered engine, the lighter, high volatility stocks help start a diesel. But the heavier, low volatility stocks have more heat or energy content, and it's that heat that the diesel uses to produce power. Well, therefore, you can easily see that a low power complaint can be caused by using number 1 diesel fuel in the summer. Another reason for low power is a restricted air intake. Now, this is usually accompanied by black smoke, since the engine is not getting enough air to burn all of the fuel. Check the air filter and the intake air system. Intake deposits should not be a problem since there is no fuel in a diesel intake. Just be sure to check for other restrictions. Restrictions in the fuel system can also cause low power. Impurities in the fuel can support bacteria growth, which form a slime that plugs up filters, fuel lines, and pump screens. Reduced fuel delivery and lower power are the result. And note the cloudiness of the fuel. What you're seeing is the actual bacteria-infested fuel. Now, this usually occurs after the truck has been standing for some time. To remove the slime, the fuel system must be disassembled and thoroughly cleaned. If the customer has their own fuel supply, the stored fuel will have to be treated with a biocide to stop the bacteria growth. Now, here's another drivability problem caused by fuel. This time, it's reduced or no fuel delivery. Now, this condition will occur in cool weather if the fuel's cloud point is too high. The cloud point is the temperature at which the waxes and paraffins in the fuel begin to solidify. The semi-solid wax can plug up the entire diesel injection fuel system, and the only way to clear the system is to warm it up to a temperature above the cloud point. Then the fuel will flow normally. Some poor grades of diesel, those with too much wax and paraffin, have been found with a cloud point of about 40 degrees Fahrenheit. While the cetane rating of that fuel was within the number 2 diesel fuel range, the cloud point was what would be expected of number 3 or 4 fuel. Some fleets mix their used engine oil with their fuel to dispose of it and to keep from buying as much fuel. GM Truck recommends that this not be done for several reasons. First, the heavier hydrocarbons may not burn completely and will carbon up the engine, causing problems such as stuck piston rings. And second, even if the oil is carefully filtered, small metal particles can get into the injection pump and shorten its life due to wear. Now, both engine oil and poor fuel can cause carbon deposits both on and in the tips of the diesel fuel injectors. Now, this can lead to uneven spray patterns, leaking or dribbling, all of which will negatively affect combustion, causing low power, smoke, and even misfiring. Another cause of poor combustion and low power is injector pop-off pressure. Over time, the injector pop-off pressure may become lower due to the loss of spring pressure. Too low a pop-off pressure will cause a change of the fuel spray pattern and generate a low power complaint. If you suspect pop-off pressure to be the cause of the problem, check the pressure by using nozzle tester J29075B. And replace the injector if the pressure falls below the specified pressure. Remember, naturally aspirated engine nozzles have a lower pop-off pressure than that of the nozzles of the turbocharged engine. Be sure to check your manual for the correct pressure specifications. Now, smoke concerns also bring diesel truck owners into your dealership, so let's quickly cover those. White smoke is normally from incomplete combustion, and a little is to be expected during cold startup and warm-up. The white smoke is diesel fuel that got hot enough to vaporize, but not hot enough to burn. A change to #1 diesel fuel in cold weather should help, as will any type of engine heater. If the white smoke continues, there is a mechanical problem, either with the thermostat and the engine is not warming up, or coolant could be getting into the combustion chamber. Black smoke shows up when there's not enough oxygen to burn all of the fuel, but the fuel gets hot enough to burn off the hydrogen components while discharging the remaining carbon, black carbon, thus the black smoke. Some black smoke can be expected under quick acceleration, but if it's excessive, look for an inlet air restriction. Too much fuel delivery due to a restricted return line or too high a pump housing pressure will also cause black smoke. Remove any restriction in the return lines and the housing pressure control to correct the excessive fuel delivery. Blue smoke is usually not a fuel problem. It's caused by engine oil getting into the combustion chamber. Either the engine is consuming its own crankcase oil or someone mixed oil in with the fuel. Eliminate the oil and you will eliminate the blue smoke. What is the solution to diesel fuel problems? Make sure that the right grade of clean, low sulfur fuel is used. Whether it's diesel or gasoline, the use of the correct grade of quality fuel can make a big difference in the drivability of our GM trucks and the engines that power them. From the 2.2-liter four-cylinder engine of our compact light-duty vehicles up to the 3116 cat diesel that powers our medium-duty trucks. Now, let me review the high points of what we've discussed. Gasoline first. Octane rating is important for the proper performance of the engine. If the fuel's octane is too low, the engine may experience spark knock. But the use of unnecessarily high-octane fuels, well, not only is more expensive than necessary, it can negatively impact engine performance. Engines that run rich, too much fuel and too little air, will suffer from loss of performance, experiencing hesitation or sag or low power. And because of the fuel-rich mix, tailpipe emissions will contain two forbidden components: unburned hydrocarbons and carbon monoxide, the tasteless, odorless, poisonous gas. And engines operating too lean, too little fuel, too much air, also suffer operating problems: hesitation, surging, acceleration sag, and rough idle. And the tailpipe emissions? Well, all of the hydrocarbons are burned, but the available oxygen isn't. Therefore, a certain percentage bonds with the nitrogen in the air to create nitrous oxides, those nasty components that create smog. Now, we discussed the positive aspects of fuel additives and the impact of deposits, from deposits on the throttle plate to those inside the cylinder. And we identified the methods for their removal. And remember, when you suspect that the quality of the gas that your customer is putting in the tank is the cause of their drivability problems, be sure to get them into a good quality detergent fuel. The drivability problems just might go away. Oh, but be sure that they give the new fuel a real chance. They need to burn at least 3 complete tankfuls before you consider more serious action. And we discussed the drivability characteristics of diesel fuel: the cetane rating, fuel grades, cloud points, restricted fuel return lines, and restricted air inlet systems. And we commented on what you can learn from the color of the smoke that comes from the tailpipe: white, black, or blue. Now, before we end this video, a word about the manual. Now, you're going to find it very useful. There's a full explanation of specific properties of gasoline, including the anti-knock index, Reid vapor pressure, and the distillation curve. There's a thorough explanation of fuel additives and how they perform. There's a section on GM trucks' position on oxygen-bearing additives. You'll find a section dedicated to the complaint, cause, and correction of 11 specific drivability problems. And wrapping up the gasoline section, you'll note that there is a glossary of over 40 gasoline terms. And finally, there's a section on diesel fuel, general considerations, and complaint, cause, and corrections of 9 different drivability problems. Be sure to reference your diagnosis charts and GM service bulletins for detailed repairs or specific conditions that can be related to fuel. Now, on that note, we'll wrap up this production on fuels and how they affect drivability. We hope that the information presented in this video production and manual will be useful to you when servicing GM trucks. Thank you.